Started talking about ionic compounds, and that is always, as we talked about, a metal and a non-metal. That is again sort of a no-brainer there. You have those two things together, we're going to get a transfer of electrons from the metal to the non-metal, creating our ions, our cation and our anion here. And that's our positive and negative guy. Again, as we talked about, when we talked about bonding, again, there is no sharing of electrons here. Is that electrostatic attraction between the charges that hold it together. And when we go with naming ionic compounds, they oftentimes are broken apart into two types. There's a type 1, basically, go this way, and a type 2 going that way. And always with naming, as we were talking about, it is always the metal that is the most important thing. It is really what determines sort of how you go about naming it. And a type 1 metal is one where we have a fixed positive charge. And for the most part, that is going to be a metal that is from group 1, 2, 3, zinc, cadmium, or silver. So if you see any of these guys there, it is basically a type 1. And that's really all you need to sort of identify once you're going to go sort of name the compound. And to name the compound, we do use the whole name of the metal pretty much, our cation. For the non-metal part, we do sort of drop the last part of the name or maybe a little bit more. And we do put IDE there. Remember, as we talked about, there is no use of any type of prefix when you are have a metal involved pretty much. So that's a pretty good rule. If you got a metal, you should not use any type of prefix. It doesn't matter how many of each of those sort of ions that you have, you'll have no prefix in this at all. And we also talked about the idea that when we do put together these ions to write an ionic compound, we do want to make sure that the charge equals 0 in the simplest way possible. That again is really for the bonding aspect that we talked about, that it will allow everybody to achieve that noble gas configuration in terms of their electrons. But if you're asked to write, for example, the formulas of the cation, this would be the proper formula for the cation. It should have a charge. And for the anion, it would be this guy here, also with a charge. Mind you, as I might have mentioned, this is not the anion formula. Again, when you're asked to write the formula for the anion, it is just one of those ions by itself is what you should write. Now, a type 2 compound is the metal has a variable charge. And that's pretty much going to be your transition metals there. Are again just to the right of those guys under the staircase. Now, the deal with these guys is that they can have a variable positive charge. So you basically have to tell the people when you're naming something what the charge is on the metal. The rest of the naming is pretty straightforward. Like type 1, you're still going to use the whole name of the metal. You're still going to use the non-metal at the end with the IDE. The additional thing that we do in the middle there is a Roman numeral. And remember that the Roman numeral is not how many of the metals you have, but it's the positive charge on your cation if you just took one of them out by itself. So if you had something like CuCl2, put the L there. And when we look at this, copper is a transition metal, so that tells me it could have multiple types of charges. The good news is you will always know the charge on whatever it's attached to. So in this case, that's Cl, which is group 7, if I remember where that's at. And there's two of them, which again is what the 2 represents. That gets us a -2 overall in terms of the negative charge. Again, to balance it out here, the copper would have a +2 charge in this case. And the name here would be copper, Roman numeral 2. And again, here, chloride. And the Roman numeral 2 is again for the charge there on the metal. Any questions on any of that there? All right. So let's continue on with our naming. Here's just a decision tree. And again, it really revolves around the metal. Either you'll need a Roman numeral or will not need a Roman numeral. And again, the reason we don't need to use the Roman numeral for type 1 is they can only form that type of charge. So it's sort of common knowledge that if you have sodium, the only thing it's going to form is a +1 charge. So let's talk a little bit about polyatomic ions. Polyatomic ions are groups of nonmetals that are covalently bonded together, but have a charge. So they are ions. So if we take something like NH4NO3 and we look at this is actually two polyatomic ions together. If we split it right there between those two, over here we have one polyatomic ion, which is NH4 plus. That one nitrogen and four hydrogens all stay together as a group and unit because they are covalently bonded together and they have a +1 charge. By the way, we drew this when we were doing bonding. It looks like this, if you remember. And it also has a special name, which is known as the ammonium ion. Now, if we look at this guy over here, this is also a polyatomic ion. This is NO3 minus. Once again, that nitrogen and three oxygens will stay together. They will move around as a unit and a group. And again, that's because they are also covalently bonded together. We drew this guy as well, I think, when we were doing some Lewis structures. It looks like this. And it also has a special name, which is known as nitrate ion. So ultimately together, polyatomic ions are kind of weird things in the sense that they are two nonmetals that are sharing electrons, but because of how they're sharing and what they have gained an overall charge, either positive or negative. And so they are really an ionic compound when you put them together. So ultimately what we're doing here is we're putting a +1 charge together with a -1 charge. And that's why when we write the formula for what we have here, we actually just need one of each of those guys put together. So these work just like any other ion. When you put them together, positive, negative, it needs to equal 0. The good news on polyatomic ions is pretty much if you have a polyatomic ion, no matter how many of them you have, you just simply use the name. So we use the whole name of the polyatomic ion. So in this case, we'd actually just call this ammonium, not to be confused with ammonia, nitrate. And that is, again, a polyatomic ion here. Any questions on that there? So what is the deal with the polyatomic ions? Well, the deal is this. For the most part, that's probably your most common positive polyatomic ion. There is the hydronium ion, which is this guy. That's the hydronium ion, which is also positive. But for the most part, there's kind of very few positively charged polyatomic ions, which means what most of the time will happen with the polyatomic ion is it's going to probably be hooked up with a metal. So most of the time you're going to have a metal and a polyatomic ion together, which basically means when we go to name these sort of compounds that's a metal and a polyatomic ion together, we actually fall back to our rules about type 1 or type 2. Again, we have a metal involved, which is always the most important thing here. So you would look at the metal again and make that decision of basically, do I need a Roman numeral or do I not need a Roman numeral? The polyatomic ion really doesn't matter in terms of the naming because you're just going to use the whole name. It doesn't matter how many there are of it. It's just going to be the whole name. Any questions on that there? So if we look at a table here, some polyatomic ions, and unfortunately, you do need to know these. Yes, so you do need to know the names, the formulas, and the charges that go with it, and that is important to be able to write the formulas if you obviously know the charges and the formulas that go with it. So, how is a good way to maybe remember these? You probably want to group things together. There are polyatomic ions that are related to each other, and that's a good way to sort of think about them. So, for example, if we looked at NO3 minus, like we saw on the previous page, once again, all those guys are staying together with a -1 charge. That is our nitrate ion. We have NO2 minus. That is what is known as nitrite. We have SO4 2 minus. That is one sulfur, four oxygens together with a -2 charge. That is sulfate. SO3 2 minus. Also sulfur and three oxygens with a -2 charge is sulfite. A vast majority of polyatomic ions will end in one of two ways. They will end in ate or ite. And if we look at these two examples, we could actually see a pattern as to sort of what is going on. So if we look at nitrate and nitrite, this has three oxygens, this has two oxygens. The one with the most oxygens in a group of two will end in ate, and the one with the least number of oxygens will end in ite. Everything else is identically the same. One nitrogen, the -1 charge, everything's the same except for the number of oxygen. Same thing here if we look at sulfate and sulfite. The only difference between these two things, they both have a -2 charge, they both have one sulfur, is the number of oxygens. Once again here, the one with more oxygens ends in ate. The one with the least number of oxygens ends in ite. So in a group of two, that's a great way to sort of remember it. So you can either remember them individually, or what a lot of people will do is understand that if you remember, for example, all the ites, if you need ate, all you have to do is just add an oxygen, everything else stays the same. Or if you want, you can remember all the eights and remember that the ites are just subtract off an oxygen, everything else stays the same. So sometimes people will just remember like one set of them, like the eights or the ites, and know how to adjust it either up or down, depending on obviously on which one that you remember. Now, there's other things that we see in here as well. There's actually groups of four that are related to each other, and these are the most common sort of group of four right about there. That is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. And in a group of four, it works the same way, except that you have two that end in ate and two that end in ite. So you could kind of break it right about there. To the right here, these are the guys that have the least number of oxygens, which means they should end in ite. So this guy is chlorite, ITE. This guy here, ClO minus, is chlorite. Obviously, you cannot have the same name for two different things. So when you get to a group of four that are related to each other, the one with the least number of oxygens will also start with hypo. And that is what is known as hypochlorite. Again, all these guys have a -1 charge. The only difference between all these guys is the number of oxygens. And that is why if we come to the left here, we have our guys that have the most oxygen. And that means that they should end in ate. So this guy would be chlorate. And this guy also should end in ate, which would be chlorate. But again, we can't have the same name for two different ones. So in a group of four, the one that has the most oxygen will also start with per. So that is what is known as perchlorate, chlorate, chlorite, and hypochlorite. You could substitute out the chlorine for anybody in the halogens in group 7, and they're named the same way. This is BrO3 minus, and that is not chlorate, but that will then become bromate. If you put an I in there, IO3 minus, it's not going to be bromate anymore. It's going to be iodate. Yeah, so you could actually swap out any of those halogens in this sort of group of four, and they're basically all named the same way, just change out the halogen part of the name. As you can see there, we have our iodate, our hypoiodite, our bromide, and our bromate there on the left. Any questions on that there? Some of the other things that you see on this list is, for example, if we take carbonate here, CO3 2 minus. This is carbonate. And if we put a hydrogen, an H plus onto it, we get HCO3 minus, +1 and -2 leaves us a -1 left over. So -2 and +1, -1 left over. This is, we basically just put hydrogen on carbonate. So this is what is referred to as hydrogen carbonate. Now, there's a historical name where they do not use hydrogen, they use bi instead, and this is also referred to as bicarbonate as well. So this is sometimes referred to as bicarbonate. The same thing happens with sulfate. You could put an H plus in front of sulfate, you'll get hydrogen sulfate, or bisulfate it's referred to as well. So that's another very common thing that you could do there. Again, not all polyatomic ions will end in ate or ite, like OH minus is hydroxide, IDE. CN minus is cyanide. So there are a few, and that are, and that is not right there. So that should be N3 on the bottom, -1 up on top. That's azide right there. So that's what that one should be. Again, has an IDE at the end of it. So polyatomic ions, you just need to learn them, yes, and know the formulas and stuff like that. And like I said, most of the time they will be attached. So for example, just to show you, how you could adjust this, obviously right here, CO3 2 minus is carbonate. Yeah. CO2 2 minus would be carbonite, right? One less oxygen, ITE at the end of it. We have our phosphate, PO4 3 minus, right? Is phosphate. PO3 3 minus would be phosphite. Again, just basically knowing if you drop down an oxygen, it ends in ITE, or obviously if you start with phosphite and add an oxygen, it ends in ATE. So you could kind of adjust some of it. That is MnO4 minus, which is permanganate, which means if I want manganate, it should be one less, yeah, because that's that group of four, right? So MnO3 minus, right? And if I want manganite, it would be MnO2 minus, and so forth. So again, you could kind of adjust up and down, if you remember how to do that. So eights and ites are just one oxygen difference. Again, if you put in the per or the hypo in a group of four, then you might be moving more than one oxygen, depending on sort of where you're starting. Any questions on that? So why don't we try some here, maybe. Whoops. There we go. Let me erase this and we'll leave it up there. Erase that. There we go. All right. So, and again, that guy should be N3 minus on the bottom. We'll do here. What is the name for the following? We'll do Fe. NO2 3. Let's do MgOH2. Let's do two CuHCO3. So what are the names of those guys? And then why don't you write the formulas for, let's do ammonium sulfide. Let's do nickel for chlorite. And let us do let's go with potassium dichromate. All right, so formulas for the guys that have names, and obviously names for the formulas there. See what you come up with here. Okay, so let's take a look at these. We'll start here on the right upper. So as I mentioned before, most of the time your polyatomic ions are probably going to be hooked up with a metal, as there's kind of not a lot of positively charged polyatomic ions. There are a few. So here's our polyatomic ion, and here in the parentheses, here is our metal. And again, once the metal's involved, that's really what's going to help us determine what's going on here. So that is a transition metal, which means it's a type 2 metal. That also should tell you it needs a Roman numeral. And we need to figure out the charge here. So we have 1 iron. Once you know your polyatomic ions, you'll know that NO2 is a -1. And once again, here there are 3 of them, which essentially, if we just add up all of our negative charge, is a -3. That means that the iron here has to carry a +3 charge. And again, that is all that we need. We're going to go with iron, Roman numeral 3. And again, that is for the charge on the metal. And once again, regardless of how many polyatomic ions you have, you just use the whole name. And that is NO2 minus, least number of oxygens there in that group of 2. And that would be nitrite. My T didn't get run over there by the there you go. Question on that one there. Now, also something that we should see and look at, right, is the parentheses do need to be put around any polyatomic ion when you have more than one of them, because we would not want to write this formula as FeNO23, because that implies what? I have 23 oxygens, which I do not have, right? So whenever you have more than one polyatomic ion, you always need to put the parentheses around the polyatomic ion, and you need to put down on the right there as to how many you have. Now, if you have just one polyatomic ion, you do not need the parentheses, although some people like to put the parentheses, but you really don't need the parentheses. It's just if you have more than one. Any questions on that there? All right, looking at the next one, once again here, that's a metal, so that's the most important thing. Here we have our polyatomic ion. The metal here, though, is magnesium, which is group 2. That means it's a type 1 metal, fixed charge. That's all I need to know. I'm going to go whole name of the metal, magnesium. And once again here, we have 2 hydroxides, but it doesn't matter in terms of the naming, and that would be magnesium hydroxide. Any questions on that one there? Again, here we have 2 hydroxides because each magnesium is +2. So we would need not 1, but 2 of those hydroxides as our anions to balance out the charge. And again, that's why the formula does look like that. Any questions on that one there? For the magnesium? No, because magnesium is group 2 and it has a fixed charge. So it's a type 1 metal. So just like we did earlier, because it's a type 1 metal, you don't need the Roman numerals. And you only need them for type 2 because they have the ability to make multiple charges. So you have to tell people what the charge is on that particular one. Here with magnesium, it's only ever going to make a +2 charge, so there's no need to include it, and you shouldn't include it for that reason as well. Other questions? All right, here we got our friend copper. I said it right. It didn't say carbon. That's good. That's copper. We're going to break that right about there. That is a polyatomic ion, which is hydrogen carbonate or bicarbonate, whichever way you like to go with that. Once again, here it is the metal that determines how we name it, and that is a transition metal. So once again, here we will need a Roman numeral. Here we have 1 copper, and bicarbonate is this formula here with a -1 charge. That means to balance it out, our copper will be carrying a +1 charge, and this would be copper Roman numeral 1 for the charge there. And again, we're going to go either way. You could write hydrogen carbonate on this one. Or you could call this copper 1. Let's go this way. Copper 1 bicarbonate instead of the hydrogen part of it. So they're both perfectly acceptable. Bicarbonate's used a lot, like sodium bicarbonate. Yes, when you have heartburn or something like that, right? You get some of that. And so that's used a lot still, bicarbonate instead of hydrogen, but either one's perfectly fine. Any questions on any of those names there? Yeah. It is, yeah, because copper is a transition metal, so it could be +1 or +2. So because it has the ability to do either, you do have to specify what it is with the Roman numeral, and it's a type 2 metal because of that. So pretty much just like we did with type 2 metals, any of those in the transition metals are just to the right, like lead and tin. Those guys will require Roman numerals. The 3 exceptions in the transition metal region is the zinc, cadmium, and silver. And again, because those guys have fixed charges, you don't need the Roman numerals again for those guys. All right, so let's do some formulas. We'll start at the bottom here since we're there. Nickel, Roman numeral 4 tells me automatically that my nickel is a +4 charge. Chlorite is ClO2 minus. So ultimately here, when we look at what we're putting together, we got a +4 and a -1. So we actually need not 2, not 3, but we need 4 of these guys basically to balance it out. And now we can write our formula. We have 1 nickel. And since that is a polyatomic ion where there are multiples, we need parentheses, and we need a 4 there on the bottom. Any questions on that there? And again, if it helps you to draw it out, because all you have to do at the end is just count, right? 1, 2, 3, and 4, right? So you could just do it that way. It's much easier sometimes. We'll go with the ammonium sulfide up on top. So ammonium is right here. Sulfide is actually just sulfur from the periodic table, -2, right? It's not sulfate or sulfite, it's a sulfide, IDE. So that's just that. So we're basically putting together a -2 and a +1. In this case, we actually need 2 of the ammonium. So because that's a polyatomic ion, we will need parentheses and the 2 and 1s basically here to balance it out. Any questions on that one there? Lastly, here we have potassium dichromate. So this is where I was talking about earlier the other day. This is the one and only place where you might see a prefix with a metal, and it's because the polyatomic ion actually has a prefix in its name. So that's the only time you'll actually see it. So the polyatomic ion here is dichromate, and because that's the name of it, and it has a prefix in its name, that's the only time you'll see it with a metal is in that case. So dichromate is Cr2O72 minus. That's dichromate. That's a lot going on there. Our friend potassium there is group 1, which is +1. So in this case, we're ultimately putting -2 together with +1. So to balance it out, we will need 1 more potassium for a total of 2. And now we're good to go. We could go with K2, which is 1 and 2, and just one of those dichromates in this case. So it looks something like that right there. Any questions on polyatomic ions and how to name them or write the formula? Essentially, pretty much you're going to fall back on your type 1, type 2 rules. And again, just use the whole name of the polyatomic ion and obviously put it together like a normal ionic compound. All the positives and negatives basically cancel each other out. Any questions on any of that there? So the next thing we're going to talk about is, I guess we'll do acids. Why not? Acids are substances that produce H plus ions in solution. H plus ions are the hydrogen ions. Hydrogen ions. It's also sometimes referred to as a proton in acid-base chemistry, and that's because, again, a hydrogen has a proton, an electron, and no neutrons. So the only way it becomes positively charged is to lose an electron, and that leaves it just a proton. So it's sometimes referred to as a proton. Oddly, since we're talking about polyatomic ions in acid-base chemistry, H plus and H3O plus are used interchangeably in acid-base chemistry, H3O plus being the hydronium ion. Now, acids and how you name acids is basically all about oxygen and basically whether or not there is oxygen in the acid. By the way, for acids, you could consider them basically ionic compounds in most cases, and the cation for all acids is H plus. So basically, H plus is always the cation, and the negative anion is obviously going to be used to balance it out, and we're going to balance out the charge to zero like normal. That is because that's pretty much your definition of an acid. An acid is something that, when it goes for a swim, has the ability to release that H plus and let it go float freely in the solution. And that's what makes something acidic or basic. For example, the ratio of H plus you have in there to OH minus. So if the acid does not have oxygen, that's right, it will start with hydro something ic acid. So that is the way that we name acids that do not contain oxygen. So for example, we have HCl. And by the way, when we write formulas for acids, we use the aqueous symbol to indicate that it's basically a solution, and it's the acid form of this. So here we do not have oxygen. The cation here is H plus. The anion is Cl minus, which is why we have one of each there in that particular formula. And that means that this guy is our friend, hydro. The missing part comes from the anion. So that is hydrochloric acid. HBr, aqueous. That is hydrobromic acid. Also, cation here, H plus, anion, Br minus in this case. The reason, again, that we do use the aqueous symbol is if I had something like this, HCl, that was a gas, that is known as hydrogen chloride gas. Yeah. But when you take hydrogen chloride gas and you bubble it through water, it becomes like a solution. And then you got free H pluses floating around. And then you have hydrochloric acid. So you should always, when you're writing the formula for an acid, you should always include the AQ symbol next to it to indicate that it is an acid when you do that. Any questions on acids with no oxygen? So let's talk about acids that do have oxygen and how we go about naming those. So if our acid has oxygen in it, it is sometimes referred to as a oxyacid because it has oxygen in it, basically. And if it does, it will contain one of our favorite things that we just looked at, which is a polyatomic ion. And as we just talked about, those polyatomic ions pretty much end in ate or ite for the most part. And if you do have oxygen in there, it is going to be that polyatomic ion, which is going to help you determine how you go about naming it. So if it has oxygen and your polyatomic ion ends in ate, the acid is something ic acid. So for example, if we look at HNO3, NO3 is our anion, which is NO3 minus. Again, our cation is H plus. NO3 minus is nitrate, ATE. That means that this is nitric acid. Yeah. You feel like you ate too much, you feel icky. Good way to remember that. Yes. So that's one way you can do it. H2SO4. SO4 is our anion, SO4 2 minus. That is also why there are two hydrogens, because the cation is H plus. So to balance it out, you need two hydrogens there to balance out the charge to 0. So that's why it's H2SO4 in this particular case. That is sulfate. That means that my acid is sulfuric acid. So again, if it has oxygen and your polyatomic ion ends in ate, you'll have ic acid. No hydro here. Yeah, so no hydro here, no mixing of the two. Hydro is only for acids with no oxygen. Yeah, so you never should use hydro with an acid that has oxygen. Now, if your polyatomic ion ends in ite, it will be something OUS acid. Oh. So if we take HNO2, which is an acid, here again, our cation is H plus. This is our anion, which is our polyatomic ion of NO2 minus. That is nitrite, ITE. That becomes nitrous acid. Yeah. H2SO3. That again is our cation of H plus. There's two of them because our anion is SO3 2 minus to balance out the charge. That is sulfite, which means this will be sulfurous acid. Any questions on that there? Again, you see here oxygen, no hydro. Yeah, so that's a very common error that people make all the time. They want to put hydro on every acid because it makes it sound more chemistry-like. It just makes it sound wrong in a lot of cases, so don't do that. Again, hydro only for no oxygen. If you do have oxygen, leave hydro off of it. But again, either ic or us. Ic if the polyatomic ion ends in ate. OUS if it ends in ite. Any questions on that there? All right, so why don't you try a couple here, and let's do something. I don't know. Let's do H2S. Let's do H3PO4. Let's do HI. Let's do actually HClO3 here. And then why don't you give the formula for let's do hydrofluoric acid. Let's do perchloric acid. Let's do hyposulfurous acid. Why not throw one of those in there, I suppose? And let us do carbonous acid there. Yeah. We'll start here on the first one. Again, this is an acid. I see no oxygen involved, so I know it should start with hydro. Remember again here that the cation is always H plus for acids. That is sulfide, which is -2, and that again is why we do have two of the hydrogens there to balance out the charge. But that's basically sulfide, so that's hydrosulfuric acid in this case, hydrosulfuric acid. Any questions on that? That in the gas phase would be hydrogen sulfide gas, if it was a gas. We come over here, bless you. Once again, here we do have our polyatomic ion. That is PO4 3-, which is phosphate. Also why we have 3 of our H pluses to balance out the charge. But that's really all we need. That is a polyatomic ion that ends in 8, which means this is going to be phosphoric IC acid here as our name. Question on that one there. Here we do not see oxygen. That is I minus. And again, in this case, we just need one H plus. So that also is going to start with hydro. And since that's iodine, hydroiodic acid would be our guy. And lastly here, this does have oxygen. So we're looking for our polyatomic ion here, which is ClO3-, H plus being our cation in this case. ClO3- is chlorate. So since that ends in 8, that means that this would be chloric acid. Any questions on any of those there? All right, so let's talk about formula going back to, I'm sorry, name going back to formula. When we have the name and we want to go back to formula for an acid, the one thing we should know for sure is our cation is H plus. So again, we're just gonna kind of put it together like an ionic compound with H plus being our positive guy. So we know there's no oxygen, so fluoric should be fluoride in this case. So again, we're gonna put that together and we just need one of each with an aqueous little symbol next to it. Gives us our hydrofluoric acid. Now, perchloric acid does not have hydro in it, and that means that it definitely is a polyatomic ion hiding in there. And because it's a polyatomic ion, the easy way to figure out which one it is, if you're not sure, is it ends in ic, which means the polyatomic ion ends in 8. So if you cross that out and kind of put 8 in there, that looks like perchlorate. So that is your polyatomic ion right there, perchlorate, which would be ClO4-. And again, always for acids, our H plus is our cation. So now we're just going to put those guys together, a little HClO4 with an aqueous symbol. So you can kind of scratch out the name, put an 8 or an I, and it'll kind of tell you the name of the polyatomic ion if you can't really figure it out from the name. Any questions on that there? Hyposulfurous acid. Oh, wow. All right, we'll do the same thing. I do not see hydro, but I do see hypo, but not hydro. So because I don't see hydro, it does have oxygen, which means there should be a polyatomic ion in here somewhere. Going to do the same thing. This ends in OUS, which means my polyatomic ion should end in ITE. Can kind of cross it out and put ITE. You got something like hyposulfite, yeah? Now, maybe you don't know hyposulfite, but you might know sulfite, right? Which is SO3 2-. We also know its partner there, which is sulfate, which is SO4 2-. So hypo is in that group of 4, right? and it ends in ite, which means it is the smallest in the group of four, which means I need to take off a oxygen here, and that would give me SO2 2 minus, which would be hyposulfite. By the way, again, persulfate would be SO5 2 minus, right? If we had to go upwards from sulfate. So per would be a 4-pack starting here. 1, 2, 3, and then persulfate would be one more oxygen than we have here, and SO5 2 minus. So that is our polyatomic ion. And again, our H plus there is going to be our cation. In this case, is -2 and +1. So we do need two of those to balance it out. And that will give us an H2SO2 formula there. Any questions on that one? So again, understanding how to kind of adjust up or down can be very helpful. Obviously, if you're dealing with polyatomic ions, or frankly, if you just forgot one, but you do remember something that's related to it, you could sort of figure out how to adjust up or down to get to what you need. Any questions on that one there? We're going to do the same thing here with carbonic acid. And again, no hydro, which means it has oxygen. It's got a polyatomic ion. Just going to kind of cross out a little bit of that OUS and replace it with ite. So that's like carbonite. That sounds very much like carbonate, right? Carbonate is CO3 2 minus, which means carbonite should be what? It's one oxygen less, right? CO2 2 minus should be carbonite, right? So again, making that adjustment down. Here we will need two hydrogens to balance that guy out right there. And that will give us H2CO2 in this case. Yeah. Question on that one there. By the way, what would carbonic acid, which was almost what I was going to write there, be? Carbonic acid should then be H2CO3, right? So again, one oxygen difference basically. H2CO3. From carbonate, carbonic acid, yeah. Question on how to name acids. All right, let's talk about naming. Yes, I think that's what we're doing. We're going to talk about now type 3 compounds. And type 3 compounds are different than everything we've been talking about up at this point. Pretty much type 3 compounds are covalent guys, are molecular compounds. These are our two nonmetals together. This is our sharing of electrons here. So this is what's happening here. Now, when we talk about molecular compounds, there are certain things that always sort of go by common names. And let's talk about those real quick. Some common names. Let's start with the one everybody misses on an exam. H2O is, it is water. Yeah. It's not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide in the morning or in the afternoon, probably either. Maybe they do. So it is water. It's not a trick question. You should put water and move on with your life, yes, and not miss out on a point. NH3, which looks very much like NH4 plus, which is ammonium. This is ammonia. Different, no charge, one hydrogen less. CH4 is methane. That is the simplest organic molecule you could have. It's the stuff that comes out of the vent there when you light your Bunsen burner. So a little methane happening there. So these guys really should go by their common names. The other sort of exception to sort of non-metal and non-metal is sort of what we talked about a second ago, and that involves hydrogen. So even though hydrogen is, in all intents and purposes, a non-metal, it kind of behaves a little bit in a lot of situations like a metal. So when we name things that have hydrogen in front, we oftentimes think of it as like H plus, like we just did with the acids. We just basically name it more like a type 1 compound. So it gets named like a type 1 compound, which means, as I wrote a second ago, if I had HCl, which was not an acid, we would think of this as kind of like H plus and Cl minus, even though they're sharing electrons really. And we would name this again hydrogen chloride. Same thing if we had HBr, again, not an acid, hydrogen bromide. We had H2S, that was a gas, as I mentioned a second ago, even though there are two of these guys and one of those guys, we would still just call it hydrogen sulfide. So hydrogen is kind of an exception in a sense. You pretty much have hydrogen sort of before another nonmetal. It pretty much will be named like a type 1 sort of metal. You just got to use hydrogen and whatever's there. And again, regardless of how many hydrogens that you have. So there's a few exceptions to our type 3 sort of conversation here. Any questions on that there? So type 3 is what you've been waiting for, maybe. Type 3 compounds, which are our two nonmetals together. This is the correct place to use prefixes. So in this situation, this is where you use prefixes. That is a mono for 1, a di for 2, a tri for 3, a little tetra for 4, a penta for 5, a hexa for 6, a hepta for 7, octa for 8, a little nona maybe for 9, and a little deca maybe for 10. Could be making those up, maybe. We'll see. So these are the prefixes that we use. Now, there are a couple of rules on these prefixes, but essentially when you have a type 3 compound, like two nonmetals together, it is absolutely positively the simplest thing to name. And it should take you literally like 5 seconds to name them. But honestly, it is a thing that a lot of people do mess up on because they try to make it more complicated than it is. Because there really is no ions, you don't have to figure out charges, you don't have to balance anything. You essentially just need to pick the correct prefix for how much is there and use the prefix accordingly. So how we name this is the first element, we go with the proper prefix and the whole name of the first element in the formula. And for the second element that's in the formula, we also go with the proper prefix. And that second element gets the nonmetal treatment where we drop the last part and we put the IDE. So basically, prefix, whole name of the first element, prefix, IDE on the second element, and that is it on that. Now, there are a couple of rules. One major rule is we do not use mono on the first name, but it is okay on the second. The other kind of thing that happens sometimes is when you take a prefix and the first letter of the element after it, you will sometimes get two vowels that back up to each other. Like sometimes you'll get a O and an O that backs up to each other, one from the prefix, one from the first letter of the element. You will also sometimes get an A and an O that backs up, also from the prefix, and then the first name of the element. In those situations, we get rid of the vowel from the prefix is typically what we do, and we just kind of write the name accordingly. So an example of both of these rules can be found right here with this guy, CO. So the first thing that you want to look at when you look at this is carbon. That's a nonmetal. Oxygen, that is also a nonmetal. That combination should tell you you're in the type 3 situation, which you should be really happy about because there's not much to do at this point. We're going to look at carbon. How many carbons are there? There's just one. The prefix for one is mono. Do I use the mono on the first name? I do not. So I just call it carbon. So that is an example of that. There's how many oxygens there? One. And the prefix for one is mono. Can I use it on the second name? I can. This would be the prefix mono. And then the oxygen gets the IDE treatment, which would be oxide. Yeah. What just happened between my prefix and my first letter? We do not call this carbon monoxide, right? We call it carbon monoxide, right? So this is a situation where we would get rid of the oxygen and call this carbon monoxide. So it's back-to-back O's, A and an O. Oddly, two I's, all good. We like two I's in a row. It's okay. You can leave two I's in a row. But pretty much OO or AO, you should drop the vowel off of the prefix. Question on that there. So there we go, as I wrote all over this page here. Obviously, that's what we just talked about here. First element first, second element second, appropriate prefixes, no mono on that first one. And there's a little table, nicer than I wrote there, of our prefixes. And obviously, there's our couple of rules there. I added methane there, came in, that's pretty good. So again, there's our rules. Instead of tetraoxide, because that's an A and an O, we would drop the A off the prefix and call it tetraoxide. And again, like we just saw there, instead of monoxide, monoxide, we drop those prefixes. All right, so let's try some here. And why don't you also give the formula for, let's do sulfur hexabromide. Let's do dioxygen and make something up that maybe doesn't exist. So let's go to dioxygen pentasulfide. And let us do trinitrogen. Let's do trinitrogen tetroxide there. Try that one. All right, so let's do names on the left there, formulas on the right for some things that might exist or not exist. I'm not sure. Let's see. Okay, so let's take a look. So again, really with any naming, you really want to identify what you're looking at. So I is a nonmetal. So is oxygen. They're both nonmetals. So once again, two nonmetals together should tell you it's type 3, and that should just be really happy because, again, there's no charges to figure out. There's nothing really to balance. It's just pretty much you need to pick the right prefix. So there are two of the iodine. So the prefix for two is di. Here we will use the whole name of the first element. So diiodine. Two I's are okay in this case. Second element, there are seven, which the prefix is hepta, and oxygen will become oxide. So this is a situation, again, where we're going to get that A and O backing up. So we're going to, again, kind of drop the A off of the prefix, a little diiodine heptoxide there. Any question on that one there? Coming to the next one, we see carbon nonmetal. We see oxygen nonmetal. Again, tells you it's type 3. Here we have only one carbon. So just like before, mono is the prefix, but we will not use it on the first name. So we're just going to go with the whole name here, which is carbon. That is two oxygens. So prefix is di, and oxygen gets the oxide treatment there. So a little carbon dioxide in that case. Any question on that name there? Here, that is phosphorus, which is a nonmetal. That is chlorine, which is a nonmetal. Again, that tells us it's type 3. Here we have just one phosphorus, so mono would be the prefix, but again, not going to use it on the first name. So full name here, phosphorus there, of our first element. For our Cl, we have 3, so the prefix for 3 is tri. And again, the chlorine gets the IDE treatment. So a little phosphorus trichloride action happening there. Any questions on any of those names? The absolute easiest thing to do, in my opinion, is this right here. As long as you understand what you're doing, because again, nothing to balance. You pretty much just need to write what it says. So as soon as I look at this, I do not see prefix, but I do see a prefix here. That tells me it's a type 3. And frankly, I just need to write what it says. No prefix on the first name means how many of them? 1. So that's an S. Hexa is 6 and bromide is Br. Just like that. Nothing to balance, just write what it says, basically. Here I see di, which is a prefix. I see penta, that's a prefix, tells me it's type 3. So again, just going to write what it says. Di is 2, oxygen is O, so that's an O2. Penta is 5, sulfide is S. So there that is, yes. And here again, we see tri and tetra, which is a prefix. So tells us type 3. Tri is 3, nitrogen is N. And tetra basically is 4. Oxygen is O. There you go. Yeah. So as I said, those probably like a half a second, maybe 2 seconds to do those. Again, if you don't overcomplicate it and don't try to balance things, don't try to do other weird things, they really should be pretty quick. You just got to write basically what it says. Any questions on type 3, guys? It is, again, the only place that you should be using prefixes. Yeah. So again, you did not see prefixes really anywhere else, and definitely shouldn't be anywhere near a metal, except for that one situation or so with a polyatomic ion. Any question on type 3? All right, last type of name we're going to talk about is, since we did an experiment on it, why not? Hydrates, right, as we talked about. Hydrates, as we talked about, have 2 parts. It's a salt that's separated with a little dot, and the water part, basically. So the salt, which is an ionic compound, part of it, is named like normal. So you would name it like normal. Either it's going to be probably a type 1 or type 2 situation happening. The water is named as hydrate for water. And we do use a prefix, like the ones we just saw, for how many hydrates there are. So like the one that we did, MgSO4 dot 7 H2Os. As we talked about, what that means is in that magnesium sulfate, as you saw, when it was crystallized in a solid form, it took some waters with it, and that was in the solid part of it. We would look at the salt part here and name it like normal. That is a metal. That is a type 1 metal, which means it has a fixed charge. So that's going to be magnesium. And that is a polyatomic ion, which is sulfate. Here for the water part of the name, that is 7. As we just saw, a prefix for 7 is hepta. And that would be heptahydrate. Yeah. Any question on that name there? If I had CuNO3 2.4H2O, what would the name of this guy be? Take a moment. Let's see. If we look at the salt part, again, we see our metal, which is the most important thing. That is a transition metal. So again, we want to figure out what the charge is on that. That is our polyatomic ion, which is nitrate, and there are 2 of them. That means that our copper here will have a +2 charge, and that means that this would be copper Roman numeral 2. And again, no matter how many polyatomic ions we have, we're just going to use the whole name, which would be nitrate. Now we're ready for our water part. Prefix for 4 is tetra, and water is called hydrate, right? So copper 2 nitrate tetrahydrate. Obviously, if you have the name like calcium, sulfate, and I'll go underneath, hexahydrate. You would do it the same way. You would look at the salt part of the name, which is calcium sulfate. Calcium is group 2, has a +2 charge. Sulfate is a polyatomic ion with a -2 charge, which means when we put it together, we actually just need 1 of each of those to balance it out, with our +2 and -2 balancing each other out. Hexahydrate means how many waters? Hexa is 6. Remember, since it's a hydrate, we'll put a little dot between the salt and the water part, right? And we'll just put the appropriate amount of waters in there. Any questions on that there? Questions on naming overall? You should now be professional namers of everything in life. Till you go to 1B or 200B, and then you'll name some other stuff that you didn't know about. Any questions on any of that stuff there? All right, that wraps up the naming.